Wednesdays, right? Gosh, I think last Wednesday I just didn't want to get out of bed. It's the same thing today. Wednesday. All right, so exam when?
Next Wednesday.
Next week.
Next Wednesday. Homework due tonight, not Friday, tonight. And there's also one due Monday. I just opened that up. So I'm following the syllabus that was used last year in this class. Maybe next year I won't have them so pushed close together, but again, I was just kind of going with the status quo this year. So Wednesday, or tonight's homework has some radical stuff on it, I think, and then Monday's homework has some substitution stuff on it. And so that, you need to know that stuff for the exam anyway, so it's not like you're wasting your time there. That should be good practice. I had a few questions about the radical reactions, and specifically allylic halogenation. So I wanted to kind of walk through a problem with you on the homework. And by the way, so regarding the homework, the next, gosh, you know, so this time, 3 weeks from now, we're done with Chem 206. It's over. And so the next 3 weeks is going to be pretty hectic, and I'm a little concerned that I'm not going to be able to create the volume of problems necessary for you to have plenty of practice. And so I'm probably going to have to go back to the book a little bit and assign some problems from that just to make sure that I'm able to get you enough practice. So I've already posted some spectroscopy problems, both IR and NMR problems on Blackboard this morning, and so I'll have more problems posted this afternoon. Also workshop tonight, 4 to 6. Okay, so regarding allylic halogenation, so I've had some questions because you can see in the solution to this one, and I'm going to have to scoot it over just a little bit. You can see that there ends up being 4... Okay, 4 products, right? So you can see there's a major product of this molecule and its diastereomer, plus a minor product of this molecule and its diastereomer. And so I've had some questions about, well, for example, if we have this starting material and we treat it with NBS, so there's multiple allylic protons, right? And I'm showing them. So here we've got a red allylic proton, and here we've got a blue allylic proton. We can abstract both to form a radical. So there's 2 possible radicals that we can form. If we abstract the red one, we're going to end up with this structure. And of course, that's resonance stabilized to give this structure right here. So this is basically, how many radicals is this right here? It's just one radical, right? These are resonance structures, and so we have a resonance stabilized radical. Just like with a carbocation, if we were to show resonance stabilization, it's just one carbocation. But in this case, it's important because what we find is now, because this is resonance stabilized, this carbon, this secondary carbon, has radical character, as well as this carbon has radical character. So then if we abstract from the blue position, what we end up with this is this radical right here, which is a tertiary radical, which is then resonance stabilized, and so this carbon has, this secondary carbon has radical character as well. So the first thing you have to do is you figure out which radical is more stable. And so between the red one and the blue one, which is the more stable radical? Blue. It's the blue one. And so that's the only one we're going to consider going forward, because we're only going to ever create the most stable radical. Now the reason that we get different products is because that most stable radical is going to be a resonance stabilized radical. And that means that we have 2 carbons that have radical-like reactivity, right? Because we know we have resonance structures where the tertiary carbon has radical character, and then we have this resonance structure where the secondary carbon has radical character. Which resonance structure is more important? Yeah, it's the one on the left, right? Because it's a tertiary radical, and so it's gonna give a greater contribution to the true nature. And so when we have a major product, the major product is going to derive from the resonance structure that is the biggest contributor, right? So that's why when we add our bromine, if we add it to the tertiary carbon, we're calling that the major structure. Of course, we can add our bromine to the front or the back, and so we end up with this product plus diastereomer. But remembering that we've still got radical characteristic here for this carbon, even though it's going to be less of a contributor, we can still form product at that carbon, and so in that case, we end up with a minor product where we add our bromine to that position. So it's really kind of like a 2-step problem. First off, figure out what the most stable radical is. Find the weakest CH bond, abstract it, Once you find your most stable radical, only consider that going forward. And so from there, you need to think about the carbons on that resonance stabilized allylic radical that have radical-like characteristic, and so we're going to end up with products deriving from those carbons. Okay? I just wanted to make sure we were on the same page for that. There's a few examples in the homework of allylic radicals where you have multiple possibilities, especially this one right here, so make sure you take a look at that. Okay. So today, what do? We finished up SN2 last class, basically, and so we started with SN1, so I think we titled it. I'm going to, I guess, retitle it. Turns out that was a total waste of our time. Roman numeral number 4, we're going to have the stepwise, I guess you don't have to write it over again. All right, so we have our stepwise mechanism, and we decided we were going to call that what? SN1. By the way, finally got new batteries in my pointer here. So happy about that. Okay. Not that you really care that much. Okay, so the first thing, we're going to basically follow the same steps as we followed last time. And so we'll just start with kinetics. All right, so that was our letter A for SN2. And so just like we named SN2 based on the rate law that we could write for it, we're going to name SN1 based on the rate law as well. Okay, so in the kinetics of an SN2 reaction, what we can have is a substrate or an electrophile that looks like this. And so the key difference between an SN2 and an SN1 reaction, again, is the timing of the steps, right? In this case, the electrophile waits and waits and waits. It's kind of like it's waiting to be picked up for a date or something, right, by the nucleophile, but the nucleophile stands it up. It never shows up, and so it just says, damn it, forget it, I'm still going out. And so essentially it just does its thing. It says, all right, I've had enough of this, I'm kicking off the leaving group. And so one thing about this waiting and waiting and waiting, and the reason it waits is because by kicking off the leaving group, what kind of intermediate are we going to form? We should form a carbocation, right? And so how stable are carbocations? They're not very stable. So this isn't the easiest thing to happen, and that's why the electrophile wants to wait around for the nucleophile. It's a lot more stable if it waits around for the nucleophile, but ultimately it just gets tired of this and decides it's going to go its own way. So we end up with a carbocation plus our leaving group. And so then the nucleophile finds that it's at the same club. And so they're out, and eventually our nucleophile, of course, is highly attracted to our electrophile, and our electrophile, I guess, vice versa. And so once we've created our carbocation, now the nucleophile will go ahead, donate its electrons. And so we end up with the same substitution product, but we go through a completely different pathway. And I guess our leaving group is still just there. Okay, so we have a completely different pathway that we're going to take. And now it's not a concerted mechanism. Our steps are happening at different times. And our electrophile had to wait around. Okay, so one thing we can say is when we think about the rate determining step, well, we've got two possibilities for the rate determining step. Which do you think is going to be the harder step to pull off, the first one or the second one? Definitely the first one, right? Because we're forming a carbocation. That's going to be an uphill, thermodynamically unfavorable process. And so certainly what we would say is that the rate determining step for this reaction is going to be the unilateral kicking off of that leaving group by the electrophile. And so what we can say is only, or actually I'll ask you, in an SN2 reaction, what was involved in the rate determining step? What molecules? All of it, right? It was the nucleophile, it was the electrophile, everything was at once. But in an SN1 reaction, what's involved in the rate determining step? Just the electrophile. In this case, the nucleophile has no bearing on that rate determining step because it's just not involved in the step. Pretty much that rate determining step is only the leaving group going off of our electrophile, and so we'll say only the electrophile is involved in our rate determining step. And so just like we described an SN2 reaction as a bimolecular process, what do you think we call this? Yeah, that is a unimolecular process. And it took some time to figure out the differences here. I can only imagine what it could have been like to do your PhD research on like SN1 versus SN2, right? Like we're kind of past that now, but someone did that. All right, so when we were at a rate law, what we have is our rate is equal, and it's going to be equal to K. What's K?
Constant.
Some rate constant. We're never going to get involved with the numbers in this class, but it's going to be some number that's unique to each pair of electrophiles or nucleophiles. In this case, it's just electrophiles, because what we find is that it's going to be the rate constant times the electrophile, but in this case, are we going to have the nucleophile in there as well? No, because it's not involved in the rate determining step. And so now, if we're to count the number of things we have involved, we see that number is just 1. And so that leads us to the name SN1, where S stands for substitution, N stands for nucleophilic, and then the 1 stands for unimolecular. So that's how we get our names SN1, SN2. It's ultimately based on how many things are involved in our rate determining step. All right, so letter B will again be stereochemistry. So I think we'll start with a very similar looking substrate as we did last time. So let's say we'll have an ethyl group, bromine, propyl, and methyl. Okay, so do we have a chiral center here?
Yep.
We certainly do. So we can, I guess we can prioritize this. We'd have 1, 2, 4, 3. And so that, we point our thumb back with our left hand, we can count 1, 2, 3. So that is S?
Yeah, it should be S.
Yeah, all right. So we've got an S stereocenter there. And of course, we're not even going to think about the incoming nucleophile in this first step. And so what we show is just going to be our bromine leaving. And so when our bromine leaves, we're going to end up with a carbocation. And the hybridization of a carbocation is what? I heard someone say, or a couple people say sp. It's sp2, right? Because we've only got 3 things connected, and then we've got an open p orbital. And so it's sp2 hybridized, which means it's going to be trigonal planar. And so what we have is a structure. We'll put our ethyl straight down, our propyl and our methyl straight up, but of course we'll indicate their geometry with a wedge and a dash. So we've got a positively charged carbocation there. And so what you can imagine is we've got our empty p orbital basically right there, perpendicular to all of our other stuff in our carbocation.
And the positive charge is in that empty field?
Yeah, I mean, it's hard, I think, to actually locate a positive charge, because a positive charge indicates kind of like the lack of something, right? But yeah, I mean, typically we would have something in this orbital and to have a neutral carbon, and in this case we don't. All right, so that means that these orbitals are going to be involved in any new bonds that we form, and of course, let's see, we'll just say that our bromine's still down there. I'm not too worried about him. So now what we're going to do is we're going to actually react with, let's say, a chloride. All right, now, when we talk about our chloride, all right, so how many lobes of this empty p orbital are there?
2.
There's 2, and is there any reason that it couldn't attack either lobe? There's not, right? And so in this case, well, if we think about where our bromine initially was, we can certainly undergo a front side attack, right? Because in this case, there's not actually anything left on the front side. So here's our front side attack, which is going to be totally possible and totally allowed in an SN1 reaction. And then we could also approach from the all-famous backside. And so we have our backside attack here. And so this is one of the downsides of the SN1 reaction, is that we can now approach our electrophile, which is a carbocation, from both sides, and that's going to mean multiple products, which, you know, who doesn't love that? Okay, so on the product that's going to result from our backside attack, we'll put our chlorine on the left, let's see, our ethyl will be pushed to the right. Propyl is up. And methyl is back. And so if we prioritize, we have 1, 2, 4, 3. And so that's in our stereocenter. And so here's an example of how we can still obtain that inversion product, right? So we know in an SN2 reaction, we only obtain our inversion product. And so in an SN1 reaction, we can also obtain that inversion product. But unfortunately, we can also have the result of our front side attack. And so in that case, we're going to push everything. And so this is kind of like a roller coaster ride for these substituents. So initially, they're over here, and so they form the carbocation, so they get pushed to the middle. But then if we do a front side attack, they get pushed right back to the left, right? And so they end up now on the same exact positions they were. Let's see. No, wait, sorry. Same exact positions they were, which would be just like this. So here we have the result of our backside attack, and of course this stereocenter must be what? Yeah, it must be S. It's the mirror image of our R product. And so here's what we refer to as our retention product. And so now we have multiple products possible based on the mechanism that we go through. If we go through an SN1 mechanism and we form a carbocation, we get both front side attack and backside attack. Yeah, Josh?
I know that in the SN2 mechanism, we discussed how due to a potential change in priority, it doesn't always have to be the same stereochemistry.
Right.
Does that still occur?
Yeah, and so we still, if we're going to determine stereochemistry, we're still going to have to just reprioritize and figure it out all over again, because again, our nucleophile might not be the same priority as our leaving group. And so in this case, we can see that the inversion product changes this from an S to R, but is that always going to be the case? No, we might have an inversion product that's still S, and likewise, we could end up with a retention product that actually changes this from S to R. So we just need to always make sure we're prioritizing our new groups over here, and then figuring out what the stereochemistry is. Yeah, Sarah?
Are your inversion product and retention products always opposites though?
Yeah, because you're going to get the different stereocenter there. And so in this case, what we end up with.
So one of them will be the opposite of your initial, but you just don't know which one.
Right, because if you're getting both possible stereoisomers, you're going to have both R and S. And so in this case, we end up with a racemic mixture. If we had a chiral center in our molecule already, we would actually have a pair of diastereomers. So again, that's just our stereochemistry info we've talked about. All right, so this is more complex. Boo. All right, so now we'll get into thermodynamics. This is the really interesting fun stuff. Okay, so, I mean, it's, I guess, point of view, but. So now we'll have structure versus rate. So we've done this with the SN2 reaction, and now we want to do it with the SN1 reaction. So what we should do, we should go ahead and think about what we have going on in our reaction. And so in an SN1 reaction, our rate determining step involves the formation of a carbocation. And so we can go ahead and draw out transition states. So let's say, how do we want to, we'll just skip that part for right now. So let's just draw an energy diagram. And so if we draw an energy diagram for an SN1 reaction, we're going to have a starting material, and we're going to have a product. Now in an SN2 reaction, how many intermediates did we have? We had no intermediates, right? Because it's a one-step reaction. How many steps is an SN1 reaction? It's 2, right? It's so backwards. An SN1 is 2 steps, and SN2 is 1 step. I don't know. It's just how it is. So in this case, we're going to have in an SN1 reaction, it's going to be a 2-step process, and of course our intermediate is going to be pretty high energy because that's going to be a carbocation. So what we see is our first rate determining step is going to be pretty high because we're forming a carbocation, And then the second step's not going to be nearly as high because we're losing the carbocation. Everybody loves that. All right, so here we've got starting material, our product, and then our carbocation intermediate. And so what we find is our rate determining step is going to be the difference in energy between our starting material and the transition state that leads to our carbocation. Oh.
Was this SN2 or SN1?
Oh, sorry. Yeah. Thank you. SN1. All right, and so when we think about what's gonna create a faster or a slower reaction, it's no longer going to be crowdedness, right? Because in a carbocation, it's not that crowded in the first place. We've only got 3 things around it. But what we can talk about is the stability of that carbocation, and we're going to see that the stability of the carbocation is going to be the predominant, or have the predominant role in determining what's favored and what's not favored. So we'll say that the stability of our carbocation determines the rates of our reaction. And so just like last time where I showed you with an example, we're gonna do the same thing here. So now let's consider a possibility. So let's say that we have some generic alkyl bromide that we'll call just RBR. So we're going to react that with water. Okay, and so what we find is this sits around for a while, and eventually we're going to end up with an alcohol product. Plus, I guess we'd end up with HBr. All right, but our Br is our leaving group, right? So we would ultimately end up with a Br minus. Let's think about how we can go from water to an alcohol. So we know that if our water attacked a carbocation, we would end up with ROH like this. And so we always want to get to a stable product. So how do we go from this to a stable product? We deprotonate, right? And so often there's going to be some deprotonation steps necessary. So you're perfectly fine just drawing a generic base, showing our deprotonation, which will lead to our OH plus HB, like that. All right, so some deprotonation steps could be necessary as we go, depending on the nature of our nucleophile. All right, so for our table, we're going to write our alkyl bromide. So our alkyl bromide will have methyl bromide to start with, and I think this is the same exact bromides we worked with last time. So then we have a secondary bromide, and then we have a tertiary bromide. All right, so again, we'll tell ourselves type of carbon. So we've got a methyl here, primary, secondary, and tertiary alkyl bromides. And so when we think about the carbocation that's going to form from these different alkyl bromides, what's going to be the most stable? Is it going to be a methyl carbocation, or is it going to be a tertiary carbocation? Tertiary, right? Because we know that's just the nature of carbocations. The more substitution we have, the more stable of a carbocation we'll have. So here, we've got our most stable, C+, and here we've got our least stable, C+. All right, so then when we finally were able to put relative rates down, which do you think is going to be the fastest, the reaction with the least stable carbocation or the most stable? Definitely the most stable. And so, interestingly enough, the relative rate here is pretty significant. It's 103,448. That can't be that precise, right? It's probably something similar to that number. Okay, and then for our secondary, we find that it's 1. And so what we're seeing here is that an SN1 reaction is highly, highly, highly favorable in cases where we have a tertiary alkyl bromide, because we're going to be going through an incredibly stable tertiary carbocation. But once we start decreasing the substitution of our carbocation, we're becoming much less stable, and so it's going to be a much slower reaction. Josh?
So between a secondary and a tertiary carbon, is it saying that it's 103,440 times more likely to form with that particular atom, or it happens 103,448 times as fast?
It's faster. So it's about 100,000 times faster, which means at the end we're going to have that many times more products that will have formed. Yeah. So very sadly, for a methyl bromide and a primary bromide, we don't actually see this take place, and so we can just say for these two, not observed. Yeah.
What's the unit of this?
It's just a number. The units are going to cancel. It's just how fast one of these forms relative to the other one. And so for every one molecule of this that forms, we will have formed 100,000 of these molecules. And it's just because this reaction is going so much faster. Yeah. So it's just a relative speed. All right. And so this makes sense if we think about an energy diagram. So what's not observed is when we have this methyl bromide or this primary alkyl bromide, the reaction just doesn't take place. Or we could say it takes place, but it takes place so slowly that we don't detect it. And so it's just because the carbocation is still. All right, so for our energy diagram here, we'll color code. Tertiary is blue, and secondary is green. And so we know that a blue tertiary carbocation is going to be way more stable. So we'll find him about there. And so then for our secondary carbocation, which is going to be way less stable, you can see that there's a pretty significant difference in those rate determining steps. So here, that's our activation energy, and then here's our activation energy for the secondary. So, pretty big difference. All right, does anyone notice a trend between when we talked about structure and rate between SN1 and SN2? It's opposite. Which reacted fastest in an SN2? Methyl, because it was crowdedness. And so the nature of this RBR is going to have a really big impact on what mechanism we follow. And so we'll summarize that trend in a few minutes. All right. So we didn't have letter D for SN2, and that's because SN1 is just not ideal. And so we'll just label this uh-oh. And then we'll say considerations. All right, so imagine a world where we start with this starting material. So we're going to have this secondary chloride. And so I tell you, hey, this is going to undergo a nucleophilic substitution reaction. Our nucleophile is going to be ETOH. What's ETOH? It's ethanol, right? Or ethyl alcohol. It's booze, if you want to really. Yeah, but it's ethanol, and so we've got CH2, CH3, and then OH. And so I'm also going to tell you that this is going to react under SN1 mechanism, under NSN1 mechanism. And so what we might expect to see form is I'm not worrying too much about stereochemistry here. We would expect this to form, right? Because we know that we're going to substitute our leaving group, which was our chloride, with our ethanol. But what's found during the course of our reaction is that we also form this product. And in fact, this product is our major product. Boo. All right, so anyone have any suggestions for why that's going to be our major product? Yeah. Yeah, and so what are the conditions that any kind of shifts, any 1-2 shifts can take place?
Yeah, it's more stable.
we have to have a carbocation, right? We have to have a thermodynamic reason for it to occur. So we're going to form a more stable carbocation. Do we form a carbocation in an SN1 reaction? We do, unfortunately. And so, really, if you're ever confused, and I think this is, I don't know, I haven't written the exam, but I kind of want to, well. So, here's the thing. If you're ever confused about where this gets started mechanistically, what's the first step of an SN1 reaction? Yeah, it leaves, and so do that. Just go ahead and do that. Do what you know, and then fill in the middle what you don't know. And so what we would have in this case is we would have a secondary carbocation. And now we would expect this to go on and react with our ethanol to end up right back there, right? And that makes total sense. But is there any shift that can take place such that we change the reactive center here on this molecule over to that tertiary carbon? Yeah, what are we going to do? Yeah, that's a 1,2 methyl shift. And so what we can do is start at the sigma bonding electrons between one of our methyl groups and the 6-membered ring and move those right over to the carbocation. And so we're undergoing a 1,2, I guess we can specify as a methyl shift. So in this case, what we end up with is now this tertiary carbocation. Is this thermodynamically favorable? Yeah, definitely. We just went from a relatively unstable secondary carbocation to an incredibly stable tertiary carbocation. And so from there now, what we can do is we can go to over here. And in fact, let's draw out the entire mechanism. So from this point, we would have ETOH. And so we're going to connect our nucleophile to our electrophile. Now, is that going to get us right to the product? No, because we've still got that proton attached, the pesky proton. And so to get to our final product, we're going to have to do what? Deprotonate. We'll have to deprotonate. And so we can do that in our final step, and of course we have a positive charge on this oxygen, which we're getting rid of. And so now that'll take us back to our major product. So, if you saw something like this, well, knowing that an SN1 reaction is going through a carbocation, you've got to consider all the things that we've learned about carbocations in the past, both in terms of their stability, but as well as what they do to become more stable, such as a 1,2 shift of some kind. All right, so what we'll say is that SN1 reactions, SN1 often undergoes 1,2 shifts, and they often undergo proton transfers. And so that's just a protonation or a deprotonation step, such as in this last one right here. We've transferred our proton from here onto our base. And speaking of proton transfers, that's not limited to SN1. So SN2 can do as well, but I would say that it's probably a little more common in SN1 reactions, and we'll see why that's the trend going forward. So as an SN2 example, you could have, say, this primary bromide react with water, and so now we're going to end up with this, which would need to be deprotonated by a generic base, or in this case, water. Either one's fine, and so we could get to that. So both an SN1 and an SN2 can require these proton transfer steps at some point. And ultimately, the moral of this story is SN1 can be messy. All right, so in most cases, our goal is SN2, and so a lot of what we're going to spend our remaining time talking about, really, in terms of exam material, is determining whether we're going to go SN1, SN2. And typically, if we can do SN2, we want to do SN2 because it's more stereo-specific, right? We get just the inversion product instead of both products being possible. So, let's have a little summary section of our SN2 and SN1 reactions. So first off, if we're going to do if we're going to do some kind of nucleophilic substitution reaction, one thing we can say is that the electrophile must contain an sp3 carbon leaving group bond. And so that's going to be kind of the first point. If you're giving a reaction and you're trying to wonder what could possibly happen, well, if you can find an sp3 hybridized carbon connected to a leaving group, chances are we're looking at a nucleophilic substitution. And so we've seen 3 different kinds of electrophiles. So we've seen, or I'm sorry, 4 different kinds. So we've seen methyls, we've seen primaries, we've seen secondaries, and we've seen tertiaries. And so in terms of crowdedness, all right, so this one we'll say it's crowdedness. And so which is more crowded? Is it the tertiary end or the methyl end? It's the tertiary end. And so in terms of crowdedness, how does that affect an SN2 reaction? Does it favor or disfavor? It disfavors, right? And so over here we can say this disfavors SN2. And so that means on the other end with a methyl where it's not very crowded, that's going to favor SN2. And then we can draw another trend, and that's going to refer to as carbocation stability. And so, of course, that's also going to increase from left to right. Now, in terms of an SN1 reaction, is carbocation stability going to favor or disfavor an SN1 reaction? It's going to favor. And so here we have favors SN1. And over on the left side, we're going to have disfavors also SN1. Okay, so do these trends pretty much go hand in hand? Yeah, right? Because if we have a tertiary substrate, we know that an SN2 is disfavored, and we know that an SN1 is absolutely favored. And so what do you think is going to happen in that sort of reaction, an SN1 or an SN2? It's probably going to be an SN1, right? Because not only is it very favored to go SN1, it's very disfavored to go SN2. And so vice versa, when we have a very uncrowded methyl alkyl bromide, we know that our SN2 is highly favored, and furthermore, our SN1 is highly disfavored or unfavored?
Unfavored.
Unfavored.
So I think it's disfavored.
Unfavorable.
You know what? I'm going to leave one un and one dis, and you guys sort it out. All right. All right, we're past it. I don't care anymore. Okay. Key point. This is our special key point right here, if I can find it. Okay, so what we're going to have are 4 possible substrates. We're going to have our methyl, our primary, our secondary, and tertiary. So methyl, primary, secondary, and tertiary. And so if we have a tertiary substrate, what do you think, SN1 or SN2? SN1. Generally, all the time. So I'll say, in general, because I'm sure you can find cases where it's not not going to be that case, but I'd say 99% of times, anytime you have a tertiary alkyl bromide, bam, SN1, you're done. You know what's going to happen. What about a methyl? SN2. It's just that easy. It's an incredibly unstable carbocation, so we're not going to have an SN1 reaction happen. We have to go SN2. What do you think about primary? Also SN2. What do you think about secondary? Uh-oh. More info needed. And I mean, we're talking like an entire lecture of info needed. No joke, that's Friday. Sorry. Okay. I'm all out of order now. Okay, so from here, let's see. Yeah, we got time to do this. Okay, so what I want to kind of point to is this is all energetics, right? And so basically anytime we have a methyl or a primary, what we're looking at is 2 energy diagrams. And so over here we'll talk about the SN2 that's possible, and over here we'll talk about the SN1s that's possible. Now we know that it's likely to undergo SN2, right? And we've already seen why versus the trends. And so let's say that we've got starting material and product. And so in an SN2 reaction, basically, we're going to have a relatively fast reaction, but when we have a methyl or a primary, we're going to find that our SN1 reaction is much higher in energy. And so we compare these two things. We compare the activation energy. And so which is lower, the activation energy for the SN2 or the SN1? Yeah, and so SN2 is favored, and it has to do basically with these two different possibilities. We can go either route, but the SN2 is just going to be so much faster because the activation energy, which is based on crowdedness, is much lower than over here in the SN1 reaction, where the activation energy is based on carbocation stability. Sorry. There we go. And so then we can do the same thing where we have our tertiary. And so again, we'll draw a couple of energy diagrams. And so we'll again have SN2 and SN1. And so in this case, for our SN1, we've got a very stable tertiary carbocation. And so what we see is, well, that's not too bad anymore, is it? So it's really low, but of course it's going to be incredibly crowded for the SN2 reaction. And so we find that this is way up here. And so again, we're just going to compare these activation energies. Bless you. And so in this case, with a tertiary substrate, what's favored, SN1 or SN2? Yeah, it's SN1, and again, it's just because it has a smaller activation energy. It means it's going to go faster, and so because it's going faster, that's the product we're going to see form. So here we've got SN1 is favored. And so really, when it comes down to is when we talk about our secondary alkyl bromide, what we find is the situation where now, all right, so we'll have same starting material, same product. We're going to find, so for an SN2 reaction, we're going to be about right here. For the SN1 reaction, we're going to be about right here. And so ultimately, which one's favored? You can't tell just based on the substrate. So now, since you can't based on the substrate, it's when we have to start taking into consideration some other aspects of our reaction. So here, neither is favored. And so this puts us a nice, pretty energy diagram about what's really going on. All right, so next up is going to be Roman numeral 5. So this is going to be our further consideration section. All right, so you're given a reaction, and so there are definitely going to be questions on the exam that give you a reaction, and they ask, all right, is this SN2 or SN1? Or it could say, what will the products be? And if it's SN2, you'll give the inversion product. If it's SN1, you'll have to give both the inversion and the retention product based on the stereochemical outcome of either. Do you have a question?
Yeah, so like that one, it's only one activation energy, wouldn't that make it more favored maybe?
For the secondary? So
and then, like the bump, like for that one you would need extra energy to make that.
yeah, and so keep in mind though, so you're talking about this bump right here?
Would that not matter?
So that doesn't matter. And basically what you can imagine is you're sitting up on top of this on a sleigh, and so you start going down, and you're going to have plenty of energy to go right back up that little bump and on down. So all that matters is going to be the highest bump, and that's why that determines the rate determining step. Because if we have later steps, I mean, you could end up with something, you could have an energy diagram that looks like this, really big step, and then who knows, lots of other things. But it doesn't matter, because as long as you get over this first taller hump, you're golden. You're going to just go right down the others, and they're not going to slow you down whatsoever. So only the highest bump matters. All right, so further considerations, and so this is going to take us pretty much through the end of the week. So again, the first thing we want to do is always determine the nature of the electrophile. And so again, methyl or primary is going to lead to an SN2 reaction. A tertiary will lead to an SN1 reaction. a secondary, either is possible. So we keep going forward. And so that takes us to letter B. And so now we're going to talk about electrophile structure, except this time more. Alright, so we know if it's a primary, a secondary, or tertiary, but there are definitely other aspects of the structure which can have an impact leading towards SN1 or SN2. Okay, so let's just make a list of electrophiles that can undergo both SN1 or SN2. And so first up on the list, I think, is pretty straightforward. It's going to be secondary electrophiles. All right, we've talked about it for about 10 minutes now. So secondary electrophiles can definitely go via either SN1 or SN2. And so an example of that would be this cyclohexyl bromide. All right, so there's a molecule that can go either way. But there are, in fact, some primary alkyl halides that can undergo SN1 reactions, even though we've said that SN1 reactions shouldn't be stable enough. So can you think of any reason how a primary might be able to undergo an SN1? Let's draw an example. So in this case, I'm going to say this one can undergo an SN1 reaction. Why do you think? We've got the double bond there, right? And so this is an allylic halide. And so what happens is if this leaves, we're going to end up with this molecule, which of course can undergo resonance stabilization to give this molecule. And so yeah, it's a primary carbocation, and we wouldn't ever expect that to be stable enough to do SN1, but here we've got resonance stabilization that's going to make it possible. So allylic halides can definitely undergo SN1 reactions. And then furthermore, this might be a new name, aryl halides can also undergo SN1 reactions. So an aryl halide is basically where our bromide is one bond away from a benzene ring. And so in that case, again, if our bromide spontaneously leaves, what we'll end up with is this carbocation, which can undergo resonance, and so we'll just say 3 other structures. I'll let you draw those out. All right, so there's 3 possible resonance structures. And so again, what we have is a primary carbocation, but that's going to be resonance stabilized, and so is stable enough to undergo an SN1 reaction. Let's ask, what about something that looks like this? What do you think, SN1 or SN2? Is it an sp3 carbon? Is that a requirement to do substitution? It is. And so in this case, we'll say neither SN1 or SN2. And so when you see a substrate, make sure that you can tell the difference between an allylic halide, where the chlorine is connected to an sp3 hybridized carbon, versus this vinyl bromide, where it's actually connected to the sp2. And so the reason we can't do substitution here is because it's an sp2 hybridized carbon is even more crowded because everything's in the same plane. And so ultimately, it's just not a possibility. What about this? Yeah, it's the same thing. Again, we have an sp2 carbon, and so neither is possible. Okay, so like I said, I'm going to have to go back to the book for some homework problems because I'm just running out of time to get stuff done. We've got our workshop tonight, 4 to 6. I've got a doctor's appointment this afternoon, but I should be back by 4. So I'll send out an email if I'm going to be a little later than expected.